This configuration file dictates the mathematical constraints of a 124 million parameter large language model. It defines the vocabulary size, the context length, the embedding dimensions, and the number of processing layers. This architecture functions as a high-precision industrial data pipeline. Every input is forced through a deterministic sequence of matrix operations. To see how this mechanism functions, we are going to trace the mathematical path of a single text string. As it is processed from start to finish through the GPT architecture, the process occurs in 3 phases. First, we quantize the raw text into numbers. Second, we contextualize those numbers through self-attention. And finally, we project the result into a probability distribution. Navigating the flow of tensors through these discrete layers allows an engineer to configure the system for different outcomes, transitioning from open-ended text generation to highly constrained classification tasks. Neural networks calculate continuous numerical values, so they cannot process qualitative human language directly. The first engineering hurdle is converting text strings into a format the network can compute. The byte pair encoding tokenizer breaks down raw text. It fractures unfamiliar words into smaller, known subword units, assigning each a specific integer ID. Those IDs act as coordinates, expanding into token embeddings, dense numerical arrays mapped across 768 dimensions. Self-attention processes data in parallel, lacking a way to distinguish which token arrived first. To provide context, we introduce positional embeddings. A secondary numerical array of spatial coordinates slides in, summing mathematically with the primary token embeddings. By adding these vectors together, the model gains a mathematical representation of both what the words mean and exactly where they belong in the sequence. With the sequence spatialized, the model uses masked multi-head self-attention to compute exactly how these words relate to one another. The primary embedding tensor divides into 3 parallel matrices. The query matrix is an active search probe for the focus token. The key matrix is an index of relevance. Their mathematical dot product generates a new grid of raw attention scores. If raw attention scores grow too large, gradients diminish, halting learning. To maintain stability, we divide the dot product by the square root of the embedding dimension, scaling down the magnitude of the scores across the grid. Through this matrix multiplication, every token in the sequence has precisely weighed its relevance to every other token. Autoregressive training faces a specific design requirement. The model processes data in parallel for speed, but it cannot access future tokens while learning to predict them. This n by n grid represents attention scores. The diagonal line is the causal attention mask. We overwrite all future token scores with negative infinity. A softmax function then compresses these into exact zeros, entirely blocking data flow from future coordinates. Zooming out, we see the layout of the complete transformer block. The attention mechanism connects directly into layer normalization and feed-forward network nodes. Layer normalization acts across the feature dimension, adjusting values to a mean of 0 and variance of 1, stabilizing training dynamics before data moves forward. Next, the feed-forward layer expands the embedding dimension to capture more complex representations of the data before contracting it back to its original size. Inside that feed-forward layer, we use a GELU activation function. Unlike a standard ReLU, GELU allows for a small, non-zero output for negative values, providing a smoother gradient. These visual data paths are shortcut connections. They provide a direct, unimpeded highway straight to the block's output. By bypassing the main processing layers, these shortcuts help maintain a consistent gradient flow during training. This allows transformer blocks to be stacked dozens of times while avoiding the vanishing gradient problem. After exiting the final transformer block, the tensor passes through a linear layer. It expands into a probability vector containing 50,257 nodes, one for every word in the vocabulary. During pre-training, we use cross-entropy loss to measure the divergence between this predicted probability distribution and the actual target word. During inference, we apply temperature scaling to control the diversity of the text. Lowering the temperature sharpens the distribution to favor obvious choices, while raising it flattens the curve, increasing the odds of selecting unexpected words. We also employ top K sampling. A horizontal threshold drops over the distribution, masking out all but the highest probability tokens to prevent the model from generating nonsensical sequences. By manipulating these probabilistic variables, engineers can shift the output behavior on a spectrum from highly deterministic logic to more creative responses. While the base model is designed for generation, we can execute an architectural shift to create a binary classifier, such as a spam detector. The first step of fine-tuning is freezing the parameters within the core transformer blocks. They turn static, locking their weights so they retain their language understanding but stop updating. Because we are no longer predicting the next word out of the entire vocabulary, we detach and discard the massive probability projection head from the end of the model. In its place, we attach a constrained classification FID with 2 nodes representing spam and not spam. We then implement a specific data constraint. We only extract the very last token of the processed sequence. This works because the causal attention mask forces data to flow strictly from left to right. As a result, the final sequence token is the only one that has aggregated contextual data from every preceding word. From quantization to causal masking and output projection, tracking the tensor reveals how these models function. Understanding these steps provides the foundational logic needed to build and adapt specialized model architectures.